Hello, everyone. Welcome to this talk. I'm Zhichuan. Before I start my talk, I have a small security concern here. As you know, S&P asked me to record a video for this talk. How would I know once my video will be played and modified? What if some attackers hacked the system and secretly placed an advertisement on top of my slides, like this one? To address this concern, we need some attestation techniques to make sure that the video playing process is not manipulated. Our OAT paper addresses a similar security concern for operations on the embedded devices. This work has been done with Ball et al. From Northeastern and Sumesh from Wisconsin Medicine. Let's learn a little bit about the problem that IoT systems are facing. Nowadays, we have a lot of smart IoT devices deployed in our homes and in factories. We can control them easily, like sending a command to turn off the net or to move a robotic arm. Let's simplify the interaction into two parts: the cloud server and the IoT end devices. The cloud server sends a command to the IoT end device. Normally, the end device would receive the command and do the operation, and send the results back to the cloud server. The questions are, how would the cloud server know whether the commands are faithfully executed without interruption, and whether the data from the device end are produced without manipulation? Existing solutions that based on attestation work like this. The verifiers send an attestation request to the prover. Then the prover do some measurements and send the signed proofs, like hash of the code section, to the verifier, so that the verifier can verify whether the firmware is modified or not. Traditional attestation can check static properties like code integrity, memory content integrity, and so on, which are very important in detecting some permanent attacks. However, these static properties cannot detect dynamic attacks that do not break the code integrity. Dynamic attacks use code reuse or data-only attacks to diverge the control flow or manipulate the results. Here is an example of a vulnerable robotic arm. The arm controller is made up of a main looper, which periodically fetches commands from the cloud server and gets status from the peripheral. If the status is OK, then it gets the function pointer based on the command and does the operation. However, the attacker can exploit the body get input interface and launch dynamic attacks to override function pointer or the command. To address this concern, we provide our solution. First, we designed a new security property, OEI, and then we introduced a new attestation scheme, OAT, that checks the property. OEI stands for Operation Execution Integrity. Ideally, a security property should capture both the control flow and data flow integrity. However, it's not even practical on desktop computers. To make it practical for embedded programs, OEI made the following adaptations. First, instead of checking the four programs, OEI focused on the operations. Second, instead of checking the global data flow integrity, OEI limited it to critical variables. In summary, OEI is a combination of operation scoped CFI and critical variable integrity. The two sub-properties of OEI are mutually complementary to guarantee the security of an operation. For example, without one, the other can be bypassed. Together, they can detect all code reuse and data-only attacks. Also, they can detect unauthorized operations. The design of OEI takes performance into consideration with operation scoping and critical variable selection. It outperforms a naive combination of CFI and DFI. There are several challenges to check OEI property: the incomplete verification of CFI, the heavy data integrity checking, and the security of the attestation scheme. Here is the high-level structure of the OAT system. It has three parts. The first part is a compiler that analyzes and instruments the program. The second part is a runtime part. It has a runtime trampoline library that takes OEI-related measurements and interact with the measurement engine inside TEE, which generate a signed attestation blob to be verified by the third part, an offline verification engine that checks whether the OEI property was met during the operation. In our threat model, we assume the adversaries can manipulate device input and public interface and mount code reuse or data attacks, or attempt to bypass OAT. We assume adversaries cannot modify firmware code, inject new code, or break into trust zone. Yeah, other assumptions include bare metal programs. Let's first look at operation scope CFI. So what is an operation? Informally, an operation is a logically independent task performed by an embedded device, like sensing task, sensing the temperature, actuation task, move a robotic arm, or control logic, like get some input and make decisions based on the input. Our operation scope is inspired by the operations-oriented design of embedded programs. They are usually event-based and running discrete and short-lived operations. Here is the general workflow of the control flow integrity attestation. The verifier sends an attestation request to the prover. The prover takes measurements of the control flow and sends it back to the verifier set. The important question is, what measurements to collect for CFI checking? Intuitively, there are two measurement schemes. The first is a hash-based approach that accumulates control flow transfers into a hash. It is fixed size, but hard to verify. The other scheme is trace-based. It records control flow transfers into an execution trace. It is unbounded size, but easy to verify. We propose a hybrid scheme that keeps the advantage of the hash and trace, but avoids their limitations. Our scheme is based on the following observation. There are three types of control transfers. First, the direct call and jump. They are determined and no need to record. The other two, like conditional branch and indirect control transfer, they are risky transfers. Among them, conditional branch and indirect call and jump are forward edges. Function returns are backward edges. This difference is important to our design. As for forward edges, like conditional branches, we use trace to record it. We use 1 bit to record the taken or not taken information. For indirect call and jump, we also use trace. We record the destination address into the trace. For function returns, it is backward edges. We use hash. We calculate a hash based on the current hash and the return address. The idea behind this is that once forward edge is recorded, we can reconstruct the control flow, and there's only one legal backward edge, so the return address can be easily computed and verified. This hybrid scheme considers both time and space efficiency, as well as verifiability. Now we see how CFI attestation works in an end-to-end system. During measurements collection, OAT compiler will analyze and instrument the operations code. For conditional jump, it records the conditional bit in the trace. For indirect branch, it records the destination address in the trace. For return, it calculates a hash based on the current hash and the return address. When attestation is done, all the trace and hash will be signed and sent to the verifier. At the verification time, the verifier will get a copy of the attestation blob and the original binary. It uses abstract execution to reconstruct the control flow with a recorded trace. It also simulates the stack and calculates a hash on the return address. Along the abstract execution, it checks whether each indirect jump conforms to the control flow graph. At the end of the attestation, it checks whether the reconstructed hash matches the one in the measurements. If not, it means a violation happened at runtime, like return address is overwritten. That is how operation scoped CFI attestation works. The second subproperty of OEI is critical variable integrity. Now we see how it works. What is a critical variable? We classify critical variable into two categories. The first category is control-dependent variable. They are critical because they can be manipulated to diverge control flow. Control-dependent variables can be automatically discovered by compiler. The second type is semantically critical variable. In the example of vulnerable robotic arm, the command variable is critical to the operation, so it is semantically critical. They need to be annotated by the developer using the attribute annotation syntax, as the red text shows. In the real-world programs, the critical variable affect other non-critical variables. This is a value dependency. If a value is critical, then the C value depends on the critical variable should also be treated as critical. This is an example of alias dependency. If C array is critical, the pointer points to the critical array should also be treated as critical. OAT compiler automatically detect and expand the set of critical variables. The algorithm starts from initial set of critical variables and iteratively find direct and indirect dependencies till the set reaches a fixed point. Once we have the set of critical variables, how do we do check is critical for performance? There are some existing techniques. The first one is data integrity techniques like DFI or WIT, write integrity test. They check every memory access instruction based on the statically constructed policy table. The second technique is data shield. It supports selected data integrity and stores them in protected region. Data shield also checks every memory read instruction. They all belong to the address-based checking because they need to check the memory access address. We propose a depth use value integrity. It is designed to be fast and space efficient. The idea is we don't check memory access address. We check critical variables value changes. The strategy is to do more during compilation and less during runtime. For example, during compilation, OAT analyzes the depth use chain of critical variable, and at define time, OAT records value. At use time, OAT checks for pointer-based data access. OAT not only checks the integrity of the pointer, but also checks the integrity of pointee and the bounds.